He's a professor at UT Austin, and where he runs the Institute for Foundations of Machine Learning. He's not wearing his hat today. I have two of those as proof that he runs this institute. He's an expert at learning theory and many other fields, and he taught me everything I know about learning theory, and I'm here because of him. I'm excited to hear about his research. Take it away, Adam.
Okay, thank you. You did not learn everything from me. Thanks to the organizers for putting together this workshop, especially Fanny and Matus. You guys have done an amazing job. It's been an incredible week of events, so it's always great to be here. The title, the original title of this talk, slightly different than what you read about on the whiteboard out there, is Efficient Algorithms for Learning with Distribution Shift. And this is joint work with Kostas Stavropoulos, who is my student at UT Austin, and Arsen Vasilian, who's going to be my postdoc. He's back there, going to be my postdoc next semester. And they're amazing and doing amazing work. So I'm privileged to work with them. Okay, this talk really is about generalization, carry on the theme that Matus wanted for the workshop. And I think that, at least in the context of machine learning theory, the following is true. When someone says to you, what does generalization mean in learning theory? I think we all default, this is not a definition, I'm not trying to be super precise, but I think we all kind of default to a scenario where you have a learning algorithm. Think about just classification for right now. It sees some training samples from a distribution D, and then it outputs some classifier H. I want to think about Boolean classifiers. Again, like I'm thinking about classification. And you know, if it generalizes, it means that the classifier that you trained on your training set, when you look at its error, its true error, its population loss with respect to this distribution D, the probability that it makes a mistake is small. Okay, and I guess throughout the talk, I'm going to be assuming some familiarity with epsilon delta learning or pack learning. But the key thing that I want to emphasize, you know, the point that I'm trying to make here, what I want to emphasize is that the training distribution D, when we think about generalization, I think we default to the case where the training distribution equals the test distribution. At least even, I don't know, Rob, maybe you tell me if I'm wrong, but that is what you were thinking about in terms of boosting, you know, thinking about this scenario. And I think it's what most of us think about. So for this talk, I want to think about a different scenario. I'm going to be talking about distribution shift, but in order to set the stage, I need to tell you an anecdote about protein engineering, which I happen to be working in. I've been working in for the last 2 years. And I want to tell you just one problem from protein engineering, or the goal in general, and that is, imagine you have a protein. So proteins are molecules. They're the basic building blocks of life, and they can be represented as amino acid sequences. Okay, so whatever this protein is, you know, K actually stands for lysine, L is leucine, I is isoleucine, V is valine, arginine, asparagine, and S is serine, and so on and so forth. There are 20 basic amino acids, and a protein can be represented as a sequence of those 20 letters. And then the goal, broadly speaking, of protein engineering is to figure out how we can actually make mutations on this protein sequence to improve its function. You know, one class of proteins are enzymes. Enzymes catalyze reactions. And it would be amazing if you could take an enzyme, look at its sequence, feed it to a model, and it would tell you, you know, if you just make these few mutations on this enzyme, it will improve the catalysis by 100x or something. And people have actually done this to great effect. My colleague, Danny Diaz, who I work with at UT, has an example where he's engineered, you know, an enzyme that degrades plastic much faster than you would expect. Okay, and what's interesting, also, you know, from an AI perspective, is that for this particular problem, I would say probably the most common approach to kind of the first step in building a model to predict the mutational effect of, you know, what a mutational effect will have on a protein, is to do some sort of self-supervised masking procedure. So, or some BERT type training. So what you do is you take hundreds of millions of protein sequences, and you mask out like 15% of the letters or residues in each sequence, and then you train a BERT type language model to predict what you know, which amino acids were masked out and where. And the most commonly used model for doing this is ESM2. They just came out with ESMC. We have a model that we just released called ISM. In case any of you actually use these models, check it out. And the metric or the loss that they look at when you're building these models in the self-supervised step is something called wild type accuracy. So what you're interested in is, can your model, when it's trained on 500 million amino acid sequences, how good is it at predicting, what was there in that particular position, which amino acids were actually masked out? Okay, does the task make sense? Any questions about that? Yeah, so this is called wild type accuracy. And there are many, many papers written that build models that try and maximize wild type accuracy of a model. And then you use its representations for downstream tasks. Yes? Yeah, that's a common one. Literally, ESM2 was random dropout. And I guess one thing that we realized while we were working together on this project is that wild type accuracy is actually the wrong thing to look at for protein engineering. It's the wrong loss. And why is it the wrong loss? Well, imagine that you had a model that was 100% accurate. Okay, you give it any protein in nature, you have a validation set, you give it any protein, it's able to predict those positions that were there in nature. This model is actually useless, because the goal of protein engineering is to engineer proteins that don't exist in nature. And if you give me a model that has 100% wild type accuracy, it's just going to give me back proteins that already exist. And it sort of defeats the whole purpose of building these models. And very interestingly to me is that, having spoken to many biologists and chemists working in this field, when they use the term generalization, they never mean generalization where the training distribution equals the test distribution. They always mean out of distribution. When you build a model that was trained on, say, enzymes, they want to know, how is it going to generalize with respect to antibodies, which is a different set, completely different set and type of proteins. And they're always interested, they're never interested in how you're doing in distribution. They only care about out of distribution. In fact, many of them, and this caused a lot of confusion, thought it was strange that the ML theory community would even consider the case dtrain equals dtest, as it would even use the word generalization for that particular scenario. And so that was very interesting to me. And having worked with them and thought about the problem now, I sort of think they're right. So then the fact that I've been thinking about, generalization as, the case where dtrain equals dtest for so long, been working in learning theory for 20 years, it really has started to make me rethink kind of what problems are we looking at, and are we even looking at the right problems? So that's one thing that I invite you to think about. Not yet, Nati. I'll get to you in a second. Okay. But it's not just, and it's not just biochemistry. Okay, if you imagine that you want to do AI for health, a common pipeline for people who want to do AI for health is, the first thing you do is you build a foundation model. How do you build the foundation model? Well, you have imagine we're detecting cancer from MRI. Well, you subsample some large database of images. You have some idea of what the training distribution looks like because you created it yourself. And you trained your foundation model on that labeled training set. And then what you'd like to do, of course, is you'd like to deploy this on some new population of patients. Obviously, there is going to be a distribution shift. And it's very disconcerting, to think that we actually don't understand very well, how is my model going to perform when it's given patients or images from an unlabeled test set that has obviously been subjected to distribution shift. And I think this is one of the major barriers as to why more models aren't actually right now deployed for AI for health tasks. Okay, Nati, you want to say something?
I'm just curious, when you said that you're rethinking, do you think that it's wrong to study that, or just think that organization is not the right word?
I'll get to that. Thanks, good question. I'll get to that right now. Okay, so so I think one thing to think about is for the case dtrain equals dtest. For the case dtrain equals dtest, is generalization the right term, or is the right term mimicry? Are we learning, or are we doing imitation? And I would say that for the case when dtrain equals dtest, for imitation or for mimicry, relatively speaking, we've had lots of progress, both theoretically and experimentally. If I want to learn a distribution of images, I can build a diffusion model, and it will work pretty well. If I would like to model in distribution English text, we can train large language models, and it works amazingly well. So I think where there's been much less success, both experimentally and theoretically, has been in the case where dtrain does not equal dtest. For example, for traditional like pack learning, if you give me your favorite concept class and tell me a distribution, I will tell you what the computational landscape is, whether it's hard, it's tractable, what the running time is. I think we pretty much know everything we'd like to know. I mean, most things meet. There are, of course, some open problems here and there, and I don't mean to downplay doing research in the case when dtrain equals dtest. There's still lots of interesting problems. My point is only that relative to that case, there's relatively little known when we're subjected to distribution shift. I don't know if that answered your question, Nati. But the main question that I have for this talk is sort of how can we train a classifier and then efficiently certify its performance on a test set? And one invariant for this talk is that I'm not going to assume anything about the test set. In fact, if you really want to get into it later, we can talk about it later, but I don't even need to assume that the test set was drawn IID from a distribution. Okay, I'm not going to make any assumptions on dtest. So that's the one invariant for the rest of the talk. Okay. So in order to address this problem and explain a bunch of new results to you, I want to tell you about this new model that we have called TDS learning. And it means testable learning with distribution shift. And it is a model of domain adaptation. And by the way, when I said that relatively little is known, there's still many interesting results in domain adaptation and learning with distribution shift. Samori has a lot of great works on it. But this is a new model that we're considering, and the goal is to be able to come up with efficient algorithms and not take any assumptions on the test distribution. So let me first briefly summarize domain adaptation. How many people are familiar with the formal model of domain adaptation? Okay, maybe a third of you. Okay, great. I'm happy to tell you what the formal model is. So in domain adaptation, you again have this training distribution D, where you get to see labeled samples. The learner gets to see labeled samples from D. D prime is also a test distribution. It may have no relationship to D, and it's also over the same domain and range, X cross -1, 1. So I'm thinking about classification. But the learner only gets to see unlabeled samples from D prime. Okay, motivated in large part by the AI for health problem. And the goal is with high probability, after the learner has seen both labeled and unlabeled samples from D and D prime, to output a classifier H whose loss with respect to D prime, the test distribution, is actually small. Not with respect to D, but with respect to D prime. That's the key, one huge difference here. And then, we're going to be assuming, just like in pack learning, we're going to be assuming that there's some underlying function class that you're trying to compete with, or that's labeling the samples. So that's always going to be script C. And in the back of your mind, think about half spaces as the canonical example. It's my favorite function class. And then we have this parameter lambda, which if you're familiar with agnostic learning is like opt. But in this case, lambda is the minimum over all functions in your class of the error of that function with respect to your training set, plus the error of your function with respect to the test set. Okay, so if everything is realizable, if everything is completely perfectly labeled by a half space, then lambda is 0. Otherwise, it's this parameter that you're trying to compete with. Yeah, and so you could think of lambda as the error of the best fitting classifier from some class script C. All right, and we want to output some, so we see these examples, we want to output some classifier since the error of H with respect to D prime is at most order lambda plus epsilon. So I'll allow you a little slack with respect to lambda, but actually we can improve that. Anyway, that's what we're shooting for. Yeah.
This half-space example, why is it obvious that the minimal error is 0? Because why would I know that the same half space is good for D and for D prime?
Oh, I'm just saying that if there is a half space that perfectly labels all of the points in D and D prime, okay, then the lambda is 0, and that problem is actually referred to as covariate shift. So even that is a very interesting setting. Okay, so I'm going to very crudely summarize most of the results in domain adaptation over the last 25 years in one slide. Most of the results are of the following form. The error of some classifier H on your test set is bounded by the error of your classifier on the training set, plus lambda, plus some notion of distance between D and D prime. Okay? So most of the results are generalization bounds of this form. And intuitively, it sort of makes sense. You want to figure out the test loss of a classifier. Well, you're going to pay the training loss. Plus lambda, it turns out lambda is unavoidable because the distribution might just flip all the labels from D to D prime. And then there's some notion of distance. How close is D to D prime? And if it's very large, you're going to just have to pay in the test error, the test loss of your classifier. Okay, makes sense. And I would further say that like one very, very common notion of distance between D and D prime is the notion of discrepancy distance. And here I've cited two kind of older, but really great and foundational papers by Ben David et al. And Mansour et al. And the discrepancy distance it's the supremum over all pairs of function f and f prime of how much they disagree on D minus how much they disagree on D prime. Okay, so it's some notion of like, of course, if D equals D prime, then this is 0. But it's some notion of how much D prime is confusing D. And if you study pseudorandomness, Russell's not here, but one way to think about D prime is that if this quantity is small, it means that D prime is actually pseudorandom for the function class C with respect to D. And it turns out that this pseudorandomness property will actually come into play later on when we talk about efficient algorithms. So it's an interesting relationship. But this is the most common, one of the most common notions of distances between two distributions. Okay, and here's the major problem, in my opinion, with these results. It's that you can't estimate this notion of discrepancy distance between D and D prime in any computationally efficient way. Okay, and this is really a bummer. Think about it. Imagine that you actually wanted to use one of these generalization bounds, okay, in practice. Imagine you trained a classifier in some training distribution D, and you want to get some estimate for what its error is going to be on this, on these unlabeled samples D prime that you have at your disposal. So you just want to plug things in to this bound. Well, and even assuming lambda is 0, okay, I can't estimate this discrepancy distance between D and D prime in any efficient way. So I literally have no idea. I have no bound at all on the test error of my classifier. I learn nothing. I gain no information. Okay, so that's frustrating. And even further, if you start thinking about it, like distributional. So in order to get a bound, you need to just assume that this discrepancy distance is small. You just have to make an assumption. And if you think, so then you start thinking about it. Sort of another point that I wanted to make is that distributional assumptions are everywhere, and they're sort of undermining provably efficient results in machine learning theory. Hold on, I'll get to you in a second. So if you think about compressed sensing, right, we assume that the design matrix is RIP or RE. Again, something that you cannot. It's NP hard to test if the design matrix is it's RIP. When we're learning neural networks, we often assume that the marginal distribution is Gaussian. You can't test if the marginal distribution is Gaussian. And it's a high-dimensional problem. You can't test. And inherently, learning algorithms is sort of an average case problem. In worst case analysis, what's sort of underappreciated is that you have an ironclad guarantee that when you run an algorithm that has a worst case analysis bound, it's a proof. I mean, you know for a fact that the algorithm is going to output something that's correct. But for learning algorithms, you don't know. I mean, you get a classifier, but it sort of depends on some properties of the distribution that you can't verify. So you're left in the situation of uncertainty. You never really know if your algorithm worked or not. Yeah, Samori.
Just trying to understand it. When you say you cannot learn, I thought the whole point of what Shai Ben David and Mori were doing was propose distances that you can actually learn from data. And you're just saying that they're expensive to learn?
Oh, so actually you can prove they're NP hard to even test.
Test.
If I want to even say my class is half spaces and I want to test the discrepancy distance, like whether it's large or small, even that is NP hard.
Because there are various results about learning it up to pretend, but I mean, not really.
Yeah, they're not, they don't come with efficient algorithms. Yeah, so this talk is about efficient algorithms. Another kind of problematic thing is, this is sort of an aside I have about thinking about assumptions is Rademacher complexity. Like imagine you wanted to get a grip on like, here we're in D train versus equals D test, but you want to get a bead on the generalization bound for your classifier. So you're like, oh, I'll just look at its Rademacher complexity. Well, you can't compute Rademacher complexity efficiently. You can't estimate it. So unless it's a cost of linear functions. Yeah.
I mean, it's as hard to compute it as it is to learn. So like if learning, I mean, you're right that in general you can't, but in general you also can't learn.
No, I mean, for even testing Rademacher complexity, you can show is like not computationally inefficient.
So it's learning is not complete.
No,
if the function class is computationally hard to learn, if the function class is computationally easy to learn from.
Yes. No, I can agnostically learn half spaces, but I can't test the Rademacher complexity of half spaces with respect to the uniform distribution.
Well, you can.
You can't. Okay, and one way that we got around this issue of not being to estimate Rademacher complexity is there was some work on testable learning that it's a beautiful model by Arsène and René Rubenfeld, where you come up with ways to actually certify the correctness of your learning algorithm without having to directly try and estimate things like Gaussianity and Rademacher complexity. And what we proved in some follow-up work with my former student Arvind Golakata and Prabhash Katari is that actually interestingly, like these models that test the assumptions that the learning algorithm needs is captured precisely by Rademacher complexity. Okay, so that sort of an aside. Let me get back to domain adaptation. Remember what we want to do. So finally, I can tell you how many minutes am I in the talk? I really wanted to get to TDS learning really quickly, but I guess it didn't happen. So finally, I can define TDS learning for you. Okay. So here's what's going to happen in TDS learning. Again, your learning algorithm, you're going to get samples from D and D prime, labeled from D, unlabeled from D prime. And you're first going to run a computationally efficient test. And if the test accepts, then you're going to output a classifier whose error is small with respect to the test set, which is what you want. And furthermore, our learner will give you a proof, a certifiable bona fide proof that your classifier really does get order lambda plus epsilon. You'll get a proof. Now the test might reject, in which case, like the learning algorithm does nothing. I mean, it just says, sorry, I'm rejecting. Okay, and right now the way that I've defined TDS learning, it's vacuous because the learning algorithm might just always reject, right? So I have to do something to make this non-trivial. So what I'm going to do is that I'm going to say if the marginal on dx equals the marginal on d prime, then the test must accept with high probability. So that's the kicker, right? So it can't always reject. If the marginal of the test equals the marginal of the train, it's forced to accept. Now, two comments. First of all, it may accept quite often, in which case you get an incredibly strong guarantee and a proof that your classifier works. It may accept in many cases. Although it is true, it is only, we want algorithms that are only guaranteed to accept when dx equals d prime of x. And maybe some of you are freaking out that this seems very restrictive and it's almost always going to reject. But we can weaken these conditions dramatically, and as you'll see in the rest of the talk. So hold your complaints about that until later. But that's the model. Any questions about the model? Okay. All right, so quiz questions. So question number one. So what I want to do is I want to convince you that when you can achieve this, it's actually a very powerful guarantee. And I also want to convince you that there's a very interesting suite of algorithms accompanying this model. Okay, so question number, why is TDS learning more general than PAC learning? Good. In PAC learning, D train always equals D test. Always, every single time. And in that condition, the test has to accept and output a classifier that does well. Okay, so yes, it's absolutely more general than PAC learning because that's an easy case. It's when it forces the algorithm to accept. And so the dream scenario is to actually take every kind of PAC learning algorithm or agnostic learning algorithm that we know and figure out a way to port it into this model so that we can be robust with respect to distribution shift. That would be a great scenario. And that's kind of the research plan that Arsène and Serbi and I and Kostas and others have been working on for the last year or so. Arson's not paying attention. Okay. Okay. Yeah.
You want to claim it's more general than pack learning?
Well, in the pack case, lambda is 0. Yeah, it's not agnostic. Yeah. As I said, we can actually get rid of the constant, but that's okay. So remember the confidence parameter delta and epsilon delta learning. Okay. Okay. Here's another quiz question. So in pack learning, how do we? This is the not the boosting case. This is the easy. What do you call this, Rob? This is like the boosting the confidence parameter. This is the easy case, right? Yeah. Okay. So in pack learning, how do we amplify the confidence parameter? You just repeat, right? Like I run my learning algorithm in pack learning, and then I can just check to see if it's done, if it's performing well on new examples. And if it's not, just run it again, like, run it a few times. You'll get one that works well. You stop. You can verify that it works well. Okay. Now think about TDS learning. Okay. Imagine that you have a TDS learner that only works with probability 51%. So you run it. You get a classifier. Now what do? I don't get labeled examples from D prime. How do I know whether it succeeded? Okay, so my point here is that even like this easy case of boosting, in the TDS setting is actually tricky. And you can do it, you can prove it. And so what you can prove is that if the failure probability is at most like 0.49, then you can amplify up to 0.99. Wait, I did that wrong. 0.51. You know what I'm saying. If it works with probability 51%, you can make it work with probability 99%. And the way the algorithm is simple, you just take majorities of classifiers, and you can do a bunch of kind of delicate averaging arguments and show that that works. But it's cool, like it's non-trivial. Okay, okay. These are the easier. Here's a slightly harder puzzle. Okay, before I get to the more difficult results. Okay, so another simple example here. So the concept class is half spaces. Lambda is 0, so there's no noise. All right. That means that the ground truth function is of the form sine of w dot x plus theta. W, which you don't know, is a unit vector. Theta is some, also you don't know, it's some real value. And I'm even going to tell you that the training marginal, d of x, is a spherical Gaussian, like simplest possible scenario. Okay, and I want to TDS learn. I want to do some TDS learning here with respect to this class. And I think the interesting case, like imagine the following happens. You get your training examples and every single label is positive. Okay. In pack learning, you would just output positive, like the constant +1 classifier, and you'd go home for the day, right? But in TDS learning, maybe D prime puts weight on points that are not labeled +1. And in a way, like it almost seems like, what can you do here? All you saw was +1. How can you, guarantee me or say something about a classifier's performance on D prime? I don't know anything about D prime. What can I do? You see labeled data from D, which is a spherical Gaussian, and labeled, and unlabeled from D prime. Yes, correct. I'm waiting for someone to figure it out. Oh, that's interesting. Yeah, that doesn't work. That does not work. That's an interesting, yeah, we thought about that too. Yeah.
If the support of D prime is contained in support of DX, then DX is probably a pretty good predictor for D prime.
Could be. That's also kind of hard to test. I'll give you a hint. You have learned something, even though you see all plus. What have you learned? You actually have learned something. What? What?
Theta.
What about theta?
It's only you have the ground limit.
Good, good. No, you learned that it's really large. Because remember, W is a unit vector. X is a spherical Gaussian. That means W dot X is distributed according to a Gaussian. If you see +1 every single time, it means that theta is large. It's like bigger than root log 1 over epsilon. It's like, theta has to be large. Otherwise, like if theta were 0, then you'd start seeing positive and negative examples. The only way you only see positive examples is if theta is large. Okay, good, very good. Now, the question is, what should I do with respect to d prime? Okay, so I can look at samples from d prime. And if I could somehow understand that d prime was also concentrated like a Gaussian, then I could also just say, okay, always say +1. Because the points from d prime are actually, they're actually also concentrated. And so w dot x, when x is from d prime, also can't be that large. But theta we know is large. So I should just accept, and I should just output the classifier all +1. Intuition makes sense? Yeah. Yeah.
For the TDS in the down boosting case.
Yeah.
Also, you just have to consider all the different cases of how many you rejected, right? And
Let's get back to that. I'll talk to you. Yeah, it's more subtle than that. Yeah. Yeah. Okay. So how do you check that d prime is actually concentrated? Well, it turns out you just need to check moments, log1/epsilon moments of d prime. And I can do that because to look at moments, I don't need labels. I just need to look, when I say moment, I literally mean, expectation, empirical estimate of x1, x2, x3, that's a degree 3 moment, and then I can look at expectation, x1, x4, x7, x10, et cetera, et cetera. Okay. So what I do is I compute all low degree empirical moments of d prime up to degree log1/epsilon. And I just check to see that they're close to what they should be if it were a Gaussian. And if they're all close to what they should be if it were a Gaussian, I accept. You can prove via a concentration argument that d prime is concentrated enough for theta to dominate. Okay, so this is sort of how these type of algorithms work. Any questions about that? All right. So what this implies is that if you want to TDS learn half spaces with respect to Gaussian distributions, non-origin centered ones, then you get a d to the order log1/epsilon time algorithm. And it turns out that this is actually tight due to an SQ lower bound that we have that also appeared in a different paper in Colt 2024. So this is in effect like the best that you can do for this particular scenario. All right, so then there are a bunch of other results that we have in TDS learning, like Rob, here's the Boolean formulas for you. Still thinking about them. Okay. So I want to tell you about some like slightly more interesting results. So, when you're developing these algorithms, what it comes down to is how can we certify that a classifier's performance on the training set transfers over to the test set? And one thing I want to point out is that distribution testing won't work. You might think in TDS learning, look, just use one of these distribution testing algorithms and check that d prime is not a Gaussian, or test that it's far close to a Gaussian. But it turns out that even for those simple problems, you need exponentially many examples in the dimension to do that type of testing. And so the only way that we can actually make progress here is to couple the testing algorithm itself with the learning algorithm. And that's how we get around these kind of generic impossibility results that come with distribution testing. Okay, so sandwiching polynomials. These turn out to be very interesting and important. Imagine f again is like your half space or some function class that you're trying to learn. Let's assume that let me define a sandwiching polynomial. So we say that it has a degree k sandwiching polynomial. If there exist polynomials p up and p down, that pointwise for every element in your domain sandwich the function f. And furthermore, the expectation of pu minus pd squared is at most epsilon. And the degree of these polynomials are at most k. Okay, that's what it means for a function to have a degree k sandwiching polynomial. And it turns out what you can prove is that if your function class admits a degree k L2 sandwiching polynomial, and the moments of d prime sufficiently and d sufficiently concentrate, then you can TDS learn this function class in time d to the order k. And for half spaces, you get d to the order 1/epsilon squared. You might say, wait, I thought we could do d to the log 1/epsilon, but that was without noise. This will handle the cases where lambda is non-zero. Theorem makes sense?
All the functions will be sandwiched.
No. Each function has two polynomials. It's like if you're familiar with bracketing, it's like bracketing, but with polynomials. Yeah. So here's the algorithm. Here's the TDS algorithm. again, you check that all of the moments of degree 2k match between D and D prime, like approximately match. And then you run polynomial regression to find the best fitting polynomial with respect to square loss on D. And now put the sign of that polynomial as your classifier. Okay, and the simple fact that we use is that for D and D prime, that 2k moment match. So if you can check that all of the moments match each other, the expectation of p minus q squared has to be approximately equal to the expectation of p minus q squared with respect to D prime. It just follows by linearity of expectation. You just expand out the polynomials, you can match all of the moments, okay? So we're gonna use this fact, and I'm going to prove to you that this simple polynomial regression algorithm actually works. Okay, do you want me to? Yeah, I know. Do you want me to prove that this? Do you want me to actually do a proof?
Yes. Yes.
Who said yes? Oh, okay. All right. All right. So live wire act. So I gotta. All right. All right. So the error of H with respect to D prime. All right. Let's see. Just by definition, that's the probability from X drawn from D prime that H of X does not equal F star of X. Okay. That's by definition. And remember, H is the sign of some polynomial P. So it's easy to prove that this probability here is less than or equal to the expectation with respect to D prime. Remember, H is the sign of some polynomial P of P minus F star of X squared. Okay, now I'm going to do, I have to do something. I have to use the almost triangle inequality. So this is at most 2 times the expectation of D prime. And I'm going to add and subtract PD. Okay, so P minus PD squared plus, what do I have? 2 expectation. I need an F star in there, right? F star minus PD squared. Okay. All right, triangle inequality. Good. Okay. This is D prime. Okay, so let's use the fact that F star has a sandwiching polynomial. What does it mean if it has a sandwiching polynomial? I know that this term can be bounded by expectation with D prime of P up minus P down squared. That's because P up, just point-wise, it's always larger than F. But notice now this D prime, because this is a polynomial, I can transfer from D prime to D. So now this is D, and as we said, by definition of having a sandwiching polynomial, this goes to epsilon. Okay, now I have to handle this term. This one, immediately I can switch to D because it's, P minus PD is a polynomial. Yeah, and then I have to add and subtract, I have to do another triangle inequality. I have to add and subtract F star again. Okay. Now, this one, again, F star is at most P up. So this goes to epsilon. And then for this term, P was the best fitting polynomial with respect to L2 regression. So in particular, this is smaller than PD minus F star because P was the one that had the smallest square loss. So it's doing better than PD. But here I am, and then I can replace this with P up again. And PD minus P up squared is at most epsilon. So everything just kills and goes to epsilon. Okay? So the key thing here was that we had these sandwiching polynomials that let us transfer from D prime to D, and also I used the triangle inequality several times. Okay. So then you can ask, well, what classes have, according to my timer, I still have 5 minutes. Yeah. So then you can ask, well, what classes have L2 sandwiching polynomials? Well, half spaces turn out to have degree order 1 over epsilon squared sandwiching polynomials. Why is that? It turns out that if you have sandwiching polynomials, you're actually fooled. There are pseudorandom generators that fool the function class via k-wise independence. And so you can use the entire literature of pseudorandomness to figure out How can I take fooling results from k-wise independence to translate them to sandwiching polynomial constructions, to translate them to TDS learning algorithms? For people like me who've thought about pseudorandom generators, it's like very satisfying. This handles decision trees, intersections of half spaces. What about constant depth circuits? Because Mark Braverman famously showed that they have L1 sandwiching polynomials, not L2. So this argument doesn't work. But in some recent work that's appearing at NeurIPS right now, these Gautam, Chandrasekaran, Vasilis Kantonis, Kostas, and Arsen, we figured out how to get it to work for L1. Okay, so I have 5 minutes left. I will briefly tell you about some harder results. Like these are kind of the easier results. Again, we'll go back to half spaces, but I'm going to assume, that again, we're looking at origin-centered half spaces, and instead of coming up with algorithms that run in time d to the order 1 over epsilon squared, I actually want fully polynomial time algorithms in polynomial in d and 1 over epsilon. And it turns out we can achieve these. At the price of paying, instead of like lambda plus epsilon, we'll pay order lambda plus epsilon. And the ingredients, it's very interesting. Like it's, I guess, the most complicated half space learning algorithm you would ever run. You first have to apply this beautiful result of Diakonikoulos, Kantonis, Zamos, and Zarifis that runs SGD on a non-convex loss, obtains some candidate hypothesis for your classifier, but it's kind of close to the classifier. And then we have to test kind of weak anti-concentration and concentration properties of the distribution using a sum of squares relaxation. But the main transfer lemma that we have is that, assume that you again have this arbitrary test set and you have some candidate hypothesis V1, you need to construct a test such that if the test accepts, then for every single vector unit direction in RD, the probability that V1, sine of V1 does not equal sine of V2 is bounded at most by some constant times their angle. So you have to prove some geometric lemma about all directions related to the initial classifier that you get. And we can show that these tests accept when D prime is log concave. And we have to do some other things, look at some spectral properties of certain projection matrices, but it boils down to kind of a geometric lemma where you have this candidate hypothesis V1, and I somehow need to verify that the mass of any error region between any other vector V2 is bounded with respect to the test distribution. In order to do that, I have to look at these projection matrices and look at some spectral properties. So we have to do a bunch of stuff. Let me tell you about some extensions. It is restrictive to only accept when D prime equals D. We were able to come up with universal algorithms. Those will accept whole classes of distributions, not just ones that are equal to your training distribution. So for example, the training distribution could be Gaussian, and our tests will accept every test distribution that is, say, log concave. Okay, so you can actually simultaneously accept many distributions. You're not restricted. We can relax that to have test distributions that, I guess the broadest result we have is that your test distribution has bounded fourth moments and has an upper bound on the density. We have new results that separate like train and test time. So if you want to spend more time training your learning algorithm, you can come up with really fast algorithms to test how it will do on D prime at test time. We can compose results from testable learning so that we don't even have to make assumptions on the training distribution either if you wanted to get rid of those. This uses the sum of squares framework to test hypercontractivity properties of the training distribution. Other recent work, we've been able to extend this not just to half spaces, but to intersections of half spaces. We can prove a bunch of SQ lower bounds. And then there's some very recent work that we submitted to iClear that works not just for classification, but for regression, neural networks. It handles interesting issues that come up if you're trying to implement a kernel method. We were able to reframe this in terms of efficient algorithms for localized discrepancy testing. As I mentioned, improve order lambda to lambda. But one thing I really want to skip this. One thing I really want to get to is a recent paper by Serbi and Abhishek Shetty, Kostas, and Arsen. They came up with a set of tolerant TDS learning algorithms that accept as long as the TV distance between D of x and D prime of x is at most epsilon. Okay, so instead of, again, just D of x equaling D prime, they can relax this. And they use a very interesting outlier removal lemma that also gives some interesting new algorithms for malicious learning. It implies efficient PQ learning, which is a model that Shafi, Adam Kalai, Yael Kalai, and Omar Montessor had come up with, where they needed an oracle for empirical risk minimization, so you can get rid of that. I'm almost out of time. As I mentioned, we have a bunch of lower bounds and separations from pack learning, like you can't learn monotone functions, indicators of convex sets. Okay, so my concluding thoughts are, I'm very excited about like TDS learning in particular, because I think that in contrast to prior works in pack style learning, in pack style learning results over the last like 2 or 3 decades, they were dominated by a handful of techniques like Fourier-based methods, boosting. And I think that there's a really wide variety of recent TCS developments that can be brought to bear on these questions, which I think is very interesting and leads to a lot of, creative opportunities for algorithm design in this space. And then again, I just want to food for thought that epsilon delta learning, maybe we should consider it mimicry. Maybe we should consider the problem solved. We have both a statistical and computational theory for it that I think is very satisfying. I definitely believe that domain adaptation is a more meaningful notion of learning. And again, like assumptions really do undermine our provable results. We like to think that provable results are better because they come with provable guarantees. But if you can't verify the guarantees that you need, then why are they better than heuristics? Again, something to think about. So I'll stop here. Thank you.
Just so that we can take one question from the audience.
One.
Okay.
Wait, someone else can go for it.
So when you talk about the distance between two distributions, are you concentrating purely on total variation distance or other notions of distance?
There are many notions. There's discrepancy distance.
MMP, for instance, like maximum mean distance, because those are very easily calculatable.
For half spaces with respect to a 0-1 loss, I doubt it.
Probably not possible.
Yeah, exactly. Yeah.
I guess you don't still.
So maybe I'm misunderstanding this, but in some ways I can view the upper and lower polynomial as coming up with a computationally efficient notion of a bracketing number.
Kind of, yes, yes,
So
exactly.
what I can basically do is, even though I can't compute these discrepancy measures, what I can do is compute sort of like a conservative or convex polar sort of relaxation of discrepancy measure, and then using this.
No, it's because it's much more restricted than discrepancy itself. It's actually what we prove is that there's some localized version of discrepancy that this corresponds to, but it is not in general. It is different than just discrepancy.
I see. So
We are not directly testing or estimating in any way the full discrepancy distance.
No, but it's like a sort of a weaker version. Like
Even that. Yeah, even that.
Okay, we'll thank Adam and take the questions in the break. We'll start the next session in 10 minutes.